Hi, good morning. Let's get started. How's everyone doing? Sorry about the confusion about which paper to review and stuff. And you got the email about my comments on the reviews, right? Some of you started to kind of express your opinion, sort of in a very timid fashion. Like, I'm not quite sure this particular thing works, but I'll yield to them. Don't yield to the authors, right? Like I said, we are trying to learn as much of what is being said for our class. So I want what you get out of the thing, right? A lot of you just had a big summary of what is said in the paper. They basically said in not so much like this, but exactly like, intro they say this, and so they basically condense the paper to 1 or 2 page worth of their summarization, right? And that's boring because you can read the original paper, right? I mean, the paper is available, so we don't need somebody to reinterpret them. It's written in English, albeit different form of English than what you're going to see for the rest of the papers. But right, so hopefully that makes sense, and hopefully we'll see when we go through the discussion what sort of a thing I'm looking for. I'm not looking for lots of text, right? I'm not going to say how much lines and all those things because it's whatever you feel is appropriate. So do you have any questions about the course logistics and stuff we covered in the last class? So this is the SOSP Hall of Fame award, and sort of within the operating system you could consider them to be like the best papers kind of thing. They started this in 2005, and we read some of these. I mean, of course, we read this in the last class and stuff. These are very old, right? So these were slightly older than me, right? So I'm guessing that nobody in the class was born before when this thing was being done, right? So this is very old. So you would think that this paper either should have had impact or the impact should be pretty remote. So if you look at the kind of hardware they worked on, it's kind of bizarre, right? It's from today's standard. It used a 27-bit architecture, right? We pretty much settled down on 8-bit machines like a while back, and none of us know that there used to be a time when the word length was weird by today's standard, right? And they use technology, they use terms which we would argue they have no idea what they're talking about, right? For example, they don't call deadlock a deadlock. They call deadlock unusual situation or something, right? But this guy must know something because he invented semaphores, right? So he kind of knew what we're talking about. So in that context, it's an interesting paper, and the community still values the stuff because a lot of things they talked about are still relevant, maybe not in the same fashion. And that's one of the reasons why we're reading those papers. A lot of those papers tend to be in that kind of vein. There are some papers which are considered so good that like we're going to read this paper, Time Clocks and Ordering of Events. It's considered extremely important. It's a relatively small paper. And Leslie Lamport swears that he didn't write the paper to talk about logical clocks. He wrote it to talk about something else. So were you there when they gave this award to him? Yeah. So even when he got the award, he swore that he didn't write about logical clocks, right? But regardless, I mean, that's what the community remembers that paper by. It's a very important paper, very small paper, but quite influential in a lot of sense, right? I just wanted to show you that so to see where the papers are. So I tried to give a little bit intro on the authors. And the other comment I made was Google and everything is available for free. So you're free to kind of look on the internet to see what others are saying. And you'll notice that a lot of the other schools are assigning the same paper, and students there are writing their reviews, right? So it's okay for you to read their reviews and see what they're saying and how that relates to what you're doing, right? It's not going to call plagiarizing as long as you don't send it to me exactly the same way and then claim that it's yours. But otherwise, use all the resources. I'm not saying that you should spend 50 hours a week on operating system, but with all the resources, you may get a wider picture. How many of you read the Unix, the further reading paper? Just, again, you don't have to read it and send me comments, but it's worth a little read. And you'll realize that once you start to use the shortcuts I was talking about, reading the abstract and all those things to get a sense of what the paper is about, it doesn't take as much time as if you had to read from top to bottom from line 1 to line n, right? Because that's going to take a lot more time. But if you try to just get a sense of what the paper is about, right? The interesting part was this: when you read this paper, the assigned paper, you get a sense that they were out in the wilderness in terms of how they're designing computers and stuff. Unix was lurking around the corner while they were writing this paper. Unix's predecessor was actually competing with this paper, right? So a lot of the ideas were not in a vacuum. There's other people working on other stuff, and some of the things that they were talking about in layered approaches and all those things was being used in Multics in a sense, and turned out that Multics did not take off, and Unix took off, right? And one of the reasons was the simplicity, not this complicated level of layering, but simplicity. So it's kind of interesting to think about the history of what happens, right? So again, for the first module, it's mostly about placing things in context of where things are. And one of the reasons I'm trying to do that is, I'm not sure how your undergrad operating system was. Most of the classes I've seen, they teach it like, they don't give you this context of why things are designed, right? They teach about semaphore as some sort of a thing which magically came from nowhere into the book, and then we kind of use it, but not in the context of where things, how things are used to solve problems and stuff. And that's part of the reason why we are trying to achieve in graduate operating system, right? One thing you realize is I'm not going to talk about any new technology that you already know from undergrad operating system. I'm not going to introduce a new concept called processes. You must have learned about processes. You must learn about threads. You must have learned about memory and all those stuff, right? So we're not going to talk about a brand new stuff. We're going to talk about the reasoning behind why things happen. So when you bump into a different problem, you can apply the appropriate solution for your system, right? I was lucky enough to actually listen to his talk like a few months before he passed away. He passed away in October 2002, and I think I heard it over the summer of 2002. To be honest, he was an awful speaker. I'm sorry, really bad speaker, right? I have no idea what he talked about. He was talking there for an hour, and I have absolutely no clue what he said, right? I have no clue whether he was talking English or he was talking in whatever language, right? He was basically mumbling, and he was just reminiscing over the stuff, what have you, right? But that's irrelevant. I mean, his work has lasting influence. This was in the first SOSP. So in the first conference, they write stuff that if you wrote any of this stuff and you send it to SOSP, any workshop that you can think of, any conference you can think of, right, it won't even go for review, right? They'll probably reject it before it goes anywhere, right? So how many of you attempted to publish papers already? So there's a few, but by the end of it, all of you would have written papers, right? Things have changed a lot since back then, because one of the things that I think till at least early 80s, when PhD students graduated, they never published papers. They published papers afterwards. You just did the work, you got a PhD, and you walked away. And you wrote papers like this, sort of, very informal. The first intro, they're ranting about how Netherlands was not conducive to do research, right? Which I think there's an interesting thing there. I mean, they're touching on some things that we still feel, but we just don't say, right? So what they're saying is basically academic research, right? If you're going to do research here, which is not technical, but it's a sort of a thing, right? If you're going to do research in a computer science department in an academic setting, right? You feel the same pain, right? Most of you are here not to advance computer science for me to build a big operating system. So if I wanted to build a big operating system, right, and I recruit, say, Nathan to write the operating system, right, there's two competing goals. He has to learn enough to kind of move along, right? He has to graduate and move off, right? So there's a point where he's like kind of learning. There's a point he becomes productive, and then he's gone, right? Which they complain as part-time workers who are not able to spend all the stuff, but you guys are part-time workers. You have classes, you have TA work, you have other stuff that you have to deal with, right? Industry labs face a similar kind of stuff. I mean, nobody wants to invest in, so we will get to that point towards the end. One of the things which bothers me is, how many of you found the whole concept they're talking about alien to you? How many of you thought it was reasonable to understand? You ignored the 27-bit and all those things, but in terms of technologies, right? Was it way out of the way? To put things in concept, right? In context, right? 20 years back, right? How did the internet look like 20 years back? How do you realize like how internet could have looked like? I'm guessing you guys are too young to know what 20 years back looked like, right? Can you imagine the internet before Google and web browser and networking, right? Those are not that ancient technologies, right? Those happened in, like, the web came about in 93 or so, right? And internet sort of came about in mid 80s and stuff, but it was largely academic kind of stuff, right? So in terms of going back 20 years, right? 20 years back, network looks so different, not just in terms of how fast you can move stuff, but all the concepts that we talk about don't exist, right? 40 years back, the world was a lot different, right? If you take the same argument, does this paper sound that ancient, right? In history, this should look like something in 2000 BC or something, right? So I don't know what that says about what we are talking about, right? And if you look at if you read the Unix paper, but that is published in 73, so the work was done in like late 60s and like around this time, right? And a lot of people still are excited about Unix, right? Because a lot of people still like Linux, which is a sort of a clone of Unix. So maybe they have invented everything. Maybe the concept that they introduced was the ultimate stuff that we should just close shop and move. But it kind of bothers me that this paper still, we can poke holes and say they don't know how to call it disk. They call it drum, right? But it's the same darn thing, right? Yeah. So those are the two things. I mean, they kind of talk about technologies in terms that we never thought about. So in terms of undergrad operating system, I just want to get a sense. I mean, I'm sure not all of you took undergrad operating systems, right? So how many of you took a course where it sort of went through the textbook and kind of presented it as it's there, not necessarily how it went about, right? How it happened, right? 3 of you. So how did the other operating system classes went? How many of you took undergrad operating system? Oh, okay. Wow, okay. So for the people who haven't taken an undergrad operating system, right, are you able to follow what's going on? What?
Hardly.
Hardly?
Hardly,
Very
very hard.
hard? Okay. So this is probably the first module is probably the simplest of the concepts, right? The later papers go much more in detail about some aspects that you should have from undergrad OS, right? And so there's a lot of discussion within the faculty on how to deal with those issues. Like, every year we get students who don't have an undergrad operating system background. They expect we used to have like a qualifying exam separate from what the course offered. So at that time we could offer some of the textbook and some of the papers and stuff because you had a separate exam for qualifying exam. So it was decided that the course, the grade you get counts as what you need to get out of this course, right? So one of the assumptions is if you're not ready, you need to take the undergrad OS, right? Right. So if you're having trouble, you may have to work extra hard to catch up because I'm kind of assuming that you have undergrad operating system level knowledge, right? So, and beginning of the course, so it may be possible for you to catch up by reading all the material from the undergrad OS and doing all the stuff, and you should do it now rather than waiting till the end, because then I'm going to grade you on what is being taught here, not the undergrad stuff, right? Yeah.
Is there any list of topics that we should cover from the undergrad OS?
Everything. So if you look at the undergrad OS from last year, the spring course I offered, I think it is silver shirts, right? So if you have that kind of knowledge, you should be fine. You should know about processes, you should know about threads, you should know about synchronization issues, right? You should know about file systems, you should know about memory management, right? Right? Because as you realize that this paper, you're probably okay because this is a very old paper, right? Any paper which is more modern than this wouldn't tell you what each technology is, right? It's going to improve on something, and you can't improve on something if you don't know what the basics were, right? I'm warning you because philosophically, I don't like to say you shouldn't be in the class, because I believe that if you're willing to work on it, I'm not going to be the one who says you can't be in the class, but you have to be realistic, right? So if you're having trouble, talk to me afterwards, offline in my office. And you should also talk to your advisor, right? Because I'm sure the students who have been here before would tell you how the qual system works, and every student kind of plans it differently, right? You need to get 3.5, which you can get in a number of different combinations, right? 1B, 2As, and 1B minus, and you guys are aware of those things, right? How the different permutations where you can get that number, right? And you kind of want to figure out which is your strengths and which is your weakness, right? If you believe that you can get B in all the courses, then you are in trouble, right? So the way it's set up, you have to get A in some classes and so on and so forth. So you kind of have to plan what it is, right? So for example, if you're interested in systems and you're really awful in algorithms, and so you have to kind of figure out what grade you're going to get there and do stuff. So if you only get B in algorithms, that means architecture and operating system, you have to get an A, right? If you have to get an A, you have to sort of have enough background to get an A. If your own skill set and what you want to do, all you need is a B here, then it's a lot more easier for how you manage that, right? Again, this is something that you should talk with your advisor. I can help you on what you should do to get around, but there's not a whole lot. I mean, I can't repeat what was said in the undergrad OS, right? So the most of the lectures for undergrad OS are in video form, so you're free to look at those to catch up. But you understand that, right? Does that make sense? Right? So for the papers, you should form a group. I mean, I didn't see any groups forming, and you need to start forming a group for your course project, right? And again, I said, try to find a complementary person, right? Try to find somebody who's good at something else, so you can kind of work off of each other, right? Does that make sense? So what's your research area?
I was in AI.
Okay.
Now in algorithms.
Okay. So I would say, if you're in algorithms, I assume that you will get an A in algorithms, right? Because it doesn't sound good if you get a B in algorithms, because you're going to do that for research, right? So if you get an A in algorithms, then you're free to, but which means that between the architecture and operating system, you have to do something. Architecture and operating systems kind of complement each other, right? There's the hardware component of the software component. So anyway, yeah. So the annoying part is when it becomes the Hall of Fame award, right? And the first page talks about how research in Netherlands kind of sucks. I mean, it's not really set for it. You probably want to take it back, right? Because it's there forever, because it's going to be assigned to all the people, and everybody's going to read about how you're complaining. But now we complain silently off the record, right? So I kind of split it into what the paper talks about and whether the paper, the way they talk about, whether it made sense in the context of when they were, right? Even though many of us were not there at the time that they were there, but we can kind of imagine what the world should have looked like, right? So when they talk about a machine which has 512 kilowords of memory in disk and 32 kilowords of main memory, right? They are in a severely resource constrained world, right? And they don't talk about how many processors they have, but they make it look like they have multiple processors. Did you get a sense of how many processors they had in the system?
Yeah. It must have been more than one, because they talked about the ability to abstract it, to abstract multiple down to make it look like one, but I don't remember saying how many.
No. I don't think they have multiple processors. I mean, it's kind of hard to imagine they had multiple processors and didn't talk about it. I think it's when you do a context switch, they want to be able to go to another thing, process or something, or maybe they're thinking of what will happen with the multiprocessors. I mean, they make it sound like each process gets a processor assigned to it, not in so many words, but in their own way. But it's not clear how many processors they have, right? So I want to look at this as in the context of what did they talk about, what is the important part, and how did it relate to where the world they were, and how does it relate to the world we are right now, right? The world we are right now is similar to them in a lot of sense and dissimilar to them in a lot of sense, right? So what do you think is the state of the world right now in terms of hardware? What do you think is a reasonable hardware for you to consider to be a modern hardware? I'm guessing most of you have some kind of hardware, right? So what do you think is reasonable? Yeah?
Multiple cores, single physical processor.
Okay.
So quad-core, dual-core systems with multiple gigabytes of RAM,
Mm-hmm.
multiple hundreds of gigabytes of hard disk space,
Mm-hmm.
video card of some kind with 3D acceleration of some kind, and a network interface, sound of some kind.
So what kind of a machine is that? Would you characterize it as?
That could be anything from a laptop, a very nice laptop, to a relatively decent desktop.
So is that would you consider that to be the modern hardware? Does the class agree that that's sort of the one that we should kind of consider? So when we're going to look at how this relates to our world, should we relate this work to the world that he mentioned, right? Is that the kind of system that you think is not the fringe, but the normal systems?
I guess it depends if you want to relate it to like personal machines or like a mainframe class machine. Processing which seems to be what they're doing.
So mainframe class, what do you think is reasonable?
Some sort of rack or two of some sort of IBM machine running with virtualization capability and Linux.
So you're talking more like a cluster kind of system.
IBM Z series, whatever you want.
So now we have like a desktop kind of stuff, and there's like a cluster server kind of stuff, right? There's somebody who's working on cluster computing or something. You are working on grid computing and stuff, right? So what is your view of your world?
So I was like cloud computing, it's like a group of like personal computer connect like to a high-speed internet, gigabit. The computer itself, doesn't have to be fast. So
It's a connected bunch of desktops kind of
Yeah.
thing. So what do you think of like blade enclosures and blade servers?
also like a big computer,
Blade,
like
yeah. So one of the things that I don't know how many of you are aware of the blade computers, right? So blades, they basically have multiple cards, but they put them into a single enclosure. So it's sort of multiple PCs inside a single enclosure with a single power supply. So it's sort of a bunch of computers within a single box, right? And that's pretty popular too, right? Then there's a mainframe, right? Mainframes were there before. They are there now. They're very important. I mean, they're a big piece of the market. We don't see them because we can't afford them. We don't need any of the uses that they do. But you can have 1 million laptops or one mainframe, right? They probably cost the same. You don't see it because it's so few, but they still out there, right? I mean, if you look at the major institutions and stuff, they still have like mainframes and stuff with lots of processors, 64, 128, and so on and so processors, right? So that's sort of like the upper limit, right? Like you can have lots of these processors into a single enclosure, call them blade something, call them mainframe something, or have like clusters and do kind of stuff, right? So what about the low end? So is the low end the desktop kind of world? So what do you consider to be reasonable low end?
Well, any kind of mobile sensor devices that are still really, really small 8-bit processors with very, very limited power and memory resources.
How many have like PDAs? How many of you have PDAs and iPhones or smartphones and stuff? So what about them?
Like the specifications or?
So in terms of the picture, right? So In terms of the number, I think actually they far outnumber your desktops, right? Or they will pretty soon, right? I mean, if you look at the projections of how much iPhone and all those are selling, right? iPhones or any of the smartphones, right? So what would you think is reasonable for one of those devices? So you said you have a PDA, right?
Let's say with a smartphone. So 520 megahertz CPU and 128 megs of RAM.
Mm-hmm.
SD storage for extra space.
Mm-hmm.
64, 128 megs of storage.
So in some sense they are similar to this one. I mean, we're still moving ahead of these things, but I'm saying when I talk about how this relates to our current world, right? Our current world in terms of numbers, the bigger one is the PDAs and smartphones, right? I mean, they sell in millions and billions. And then you have the desktops and laptops. Then you have servers and stuff. And then you have mainframes and stuff, right? In terms of the dollar per unit, probably the mainframes are more important. In terms of how much effort you put in and start doing research and stuff, the mainframes may be it. But we don't have to restrict ourselves to, we have a lot more variety than what they talked about. So I want you to keep that in mind when you talk about in the entire class, right? Modern world is much more diverse than what they had. But the good thing is our low-end machines are sort of similar to where they were. So some of the things that they talked about may actually happen in our own machine, right? So many of your smartphones may not have the I/O controller, memory unit to actually do paging, virtual memory, and all those things. So they may actually look like some of this stuff, right? So that's what we're trying to say. So Dijkstra invented, so what they talk about, right? They talk about the semaphores in the appendix, because as they complained that the program committee wanted them to talk about semaphores, so they were forced to talk about it, right? If you read the appendix, they complain a lot, right? And one of the complaints was they were forced to talk about semaphores, right? And I'm not going to say much about it because it must have been, burnt into you in an undergrad class, right? I mean, they call it P and V. I like to call it signal and weight because it's a lot easier in English than P and V, which I guess meant something in Netherlands. Dutch, okay. And yeah. So it's very hard to comment anything about it because it's so normal, right? How many of you were taught semaphores as some sort of a controversial thing, and how many of you were taught as if that's you don't ask, if you say, why do we have to learn about semaphores, right? The attitude at this point is, I mean, how else can you be a computer science major without knowing what semaphores are? Because that's so prevalent, right? So they invented it. So let's skip that for now because we can come back to it because it's so novel, right? They talk about other stuff, right? They talk about page relocation, right? So they don't say it in the way we would call it, but basically you can move the pages and bring it back into some other place, and you can relocate the stuff. So the programs only call it as segments, and you're able to relocate it to a different location, which means that in the drum you can store it anywhere, and you can restore it back anywhere, right? And which is sort of what we call as relocation. And they talk about virtual memory, even though they kind of backtrack after a while because it gets too complicated. But essentially you can have your virtual memory or segment memory to be bigger than what your physical memory and the disk memory was, right? They're still trying to understand what that is, but not really go into much detail. They talk about the layers, right? I'm not so concerned what those different layers mean because those are details. I mean, they came up with some, layer 0 has to do with the processor allocation, layer 1 has to do with something else. But I think underlying all that, they're trying to kind of get a grasp on how things should happen, right? I mean, things are becoming complex, right? Which is kind of hard to understand from our perspective because they had so little memory, it can't possibly be as complex as your Windows Vista or something, right? I mean, it's just like way more complex. But things are getting complex, and they had a relatively small group, so they had to think through all this stuff, and they figured that proving and understanding how things work is very important. So you need to kind of get a handle of stuff. So you need to be able to test stuff. You need to be able to prove stuff. So you need to kind of compartmentalize and say different modules. So you can test the different ones. So you can kind of say, something should do some, processor allocation. and abstract away all the details under that layer, right? So that layering concept was described, but essentially I think they were trying to grasp on how do you develop these systems, right? And towards the end in the conclusion, they talk about how they talk to industry folks who kind of shoot them off because they said, you're able to do this in your system because your system was a lot simpler, right? More modern, complex operating systems, I suppose they're talking about Multics, which is sort of their brethren from a whole bunch of companies who are developing those. They couldn't possibly do this stuff. They couldn't possibly be able to prove logically what's happening with the system. So, they said kind of go away, right? I think this is very important. Do you think it's important? How do you think operating systems are developed now? How do you think they should be developed now? How do you think you manage? Operating system is an example of a large project, right? I mean, your modern database is humongous. Your modern anything you can think of is humongous, right? What they were trying to wrestle with is important, right? What they're trying to wrestle with is how do you, it's sort of like what we call software engineering kind of stuff. The other stuff that they're talking about is being able to verify the logical soundness of the system, right? Being able to say something about how good the system is, being able to say if it follows some specs and stuff, right? And later work, he actually tried to prove these stuff. I mean, tried to be able to mathematically prove. I mean, obviously these people came from math because that's where traditional computer science came from. So they were trying to get a handle of how things work in some sort of a provable fashion, right? Are we there yet? Are we close? Or do you get a sense? Do you know what is the things are becoming more complicated, right? I mean, I think that we all agree. I mean, things are a lot more complicated. So whatever they faced then would be a lot more applicable now, right? Yeah.
It seems like, at least in my experience, the reality is nobody is developing things nobody tries to envision the final product before they start. Mm-hmm. And you can't do that kind of layered approach unless you think through the entire project before you start it. And I think when you think about things like Unix and Linux and Windows, I mean, they add things as they're needed, they fix things as they break, mm-hmm. and you can't, it's hard to keep to that kind of structured setup mm-hmm. when you're doing that. And I mean, probably a lot of commercial systems, not just operating systems, have mm-hmm. that problem. But when you can do it, it makes everything you do so much easier down the line. Mm-hmm. But it's hard to stay on top of it.
Yeah, my sense is it's not solved. I mean, people still earn for the time when things are simple and I can understand what's going on. I can do what they were trying to do, right? And part of that is the notion of microkernel, nanokernels, hexakernels, and all those things. We'll see a little bit of those. But it's not over. I mean, people still understand these problems a lot more than what they had to face. Yeah, people still see if you can kind of get the best of both worlds, right? And most of the papers in SOSP, I mean, a lot of papers now still deal with these issues. How do you make the compartmentalized error? How do you kind of say something, right? But by and large, the notion of proving mathematically whether the system works or not is kind of gone out of fashion. Not because it didn't go out of fashion, it's just that people didn't know how to proceed, right? It was easy to show for these kind of systems. And one of the things so they had to kind of control everything. They probably talked about everything. They kind of had real control over everything. But in real systems, you don't have that much control. You don't have a bunch of people sitting and understanding everything about all the layers and what the interactions should be, coming up with a good system. And mathematical analysis of anything approaching this stuff is just way beyond what we can do. So it's kind of gone by the wayside. Yeah.
I was just going to say, it seems that with modern operating systems, you can't really begin to even do that because it's kind of like the Lamberson paper. Our operating system today provides so much mm-hmm. in service in terms of users and applications mm-hmm. that mm-hmm. we have to go to a much simpler OS if we want to do that.
One of the conundrums that they don't have to address, and which we, like a company like Microsoft has to agree, is in their setup, they can proclaim that this is what you should have, right? The application should have this abstraction, and that will make your life good. So you as application developer should have this abstraction, you're kind of good, right? Whereas in Microsoft kind of thing, I mean, there's like multiple players involved. So Microsoft cannot just impose their view of what is good. So they cannot say, we'll only provide 2 function calls and that's it. We'll provide semaphores. Anything else you want to do, you're on your own, right? We can say from a provability point, this is all you need, but practicality means that you need to kind of incorporate all the stuff. So once you add functions and make this thing complicated, it's kind of hard to go back. The other nice thing, which they don't really stress, but I think it's far more important in later papers, which we'll see, is the notion that once you have synchronization, it's kind of hard to figure out why they even bother about multiple processors, because I never get a sense that they actually had more than one processor, but at least they're thinking about it, right? So if you have more than one processor, they kind of stumbled upon or figured out that they all can go in different speeds, right? Each of them process in different speeds. So if you're tying yourself to the time it takes for a certain operation to happen, right, then you get into trouble. So if you assume that both of them, the actual time that they are running, if they're important, then you get into trouble. But if you have this, obviously they don't use these words, if you have these primitives to kind of make sure that at certain synchronization points something should happen, and you can say something about those stuff, how fast you get there makes no difference. The order of how you make things becomes more important than the speed at which you go from point A to point B, right? As long as you can get to this stuff, you're kind of okay, right? They don't talk about it in this fashion. The Leslie Lamport paper would talk more about what we call logical clocks and causality and all those things. But essentially the idea here is you don't have to worry about the speed in which each of them run, as long as you can organize it in a certain fashion where you make sure that at the synchronization point something happens. Between them, you don't have to worry about it, right? That has a phenomenal impact on what we do. I mean, that basically allows you to schedule processes in different fashion. You don't have to guarantee that they're running at a certain speed, right? We take this for granted. I mean, that's the reason why we can do all the worry about the locks and other primitives. But the notion, so it's very nice to see them talk about this stuff, many of which sounds so obvious to us. Them talking about it in a world where none of them should have made sense, right? Most of you, when you buy a laptop these days, I don't know if you can even buy a single core processor, right? Can you buy a single core laptop these days?
Yeah, they hold single cores.
They do?
Yeah, probably one core is just broken, they sell the other part.
I'm sorry?
They hold the single core
Okay.
processor right now.
Oh, they do?
Yeah.
Oh, okay. But why? Right? Because
It's very cheap, probably. So basically, initially there was 2 cores, right?
Yeah.
One was malfunctioning, so
Oh.
they sell the other part.
So it's a dual core, but they turn off the.
One is not working already.
Okay. No, not those. I'm saying like a single core processor, right?
So the cellular processors are, I believe, usually single core. So
Okay.
Intel has like a low power CPU called Atom.
Oh,
That is single core.
So Atom, it gets into the handheld kind of thing, right? Atom I would consider to be more of going towards commodity, like a PDA kind of processor, right?
Oh, they make laptop with it.
They do?
Yeah, Acer has it.
Who?
Acer and Asus.
Okay. But those are the super small ones, right?
It's like 9 and 10 inches.
Okay. Yeah, those laptops are okay. So, and you probably the one that Sony makes, like this little ones too, right? They probably use those, right? But for most normal use, dual core seems to be normal. If you look at the ads for the the laptops and stuff, you probably get like $500 for dual core kind of stuff, right? So, which means is all the things you're talking about, synchronization, all those things, you have to face. Otherwise, there's no point in having dual core, right? But it's kind of interesting to see them talk about all this stuff, and it shouldn't have made sense to them, right? So let's look at the context of what was happening, right? It's not the dark ages. The computers have been around for a while, and they were building very nice computers. They're building multics, which was supposed to be the operating system, right? It was supposed to be the operating system for everything. It was a bunch of consortium of companies, and I think AT&T, Burroughs was there. Some of the companies no longer are in the computer business. They were building this stuff as the kind of computer, right? It could solve everything you can imagine, and like I mentioned, it turned out that it was way complicated, it was way slow, it was not agile enough to move to different stuff, but there were a lot of work going on, right? So it's not entirely dark ages, but I think one of the things which was happening was when people wanted all this perfect system, they're trying to build this more and more complex system, like what they kind of bumped into it because they didn't have enough full-timers working on the project, and what others from the Unix world came into it, right? Unix came into it because the Multics project was shut down, right? People who worked on Multics had nothing else to do. They had all these ideas that they learned from Multics, but they couldn't do anything with the Multics. I mean, the system was pretty expensive, the hardware was pretty expensive. So some of these people who still liked what the Multics was, I think Thompson was the guy, right? So he just wanted to, he took a what we call laptop now, but probably a refrigerator size personal computer in the basement, wrote the stuff in assembly language, right? And the hardware defined that he couldn't come up with, he couldn't bring the entire Multics into it. So he had to kind of make it simple. So he, rather than being the multi part, he had to make it Unix part, right? It was simple. They had to get rid of a lot of stuff. Back then, they wanted the file system to do everything. File system was supposed to, help you with everything. So if you want a database kind of semantics, it'll give it to you. If you want a blah, it'll give it to you. So it could do index files, it could do relational files, it could do sequential files. Because this one is supposed to be the end all. So it's supposed to give you anything you can want. The file system was perfect, it could do everything. The security system was perfect because it had multiple levels. So you can have not just super user and normal user, you can have different levels, right? And you can have different levels and say, you are God, and you are God -1, God -2, God -3. So you can have different levels of stuff. So this one was very pretty, and they said, fine, but that's too complicated. I'm just going to build something where I only two levels. So system administrator, the rest of us, right? I'm going to build a file system where it had no structure. It didn't care what it is. It just took files. It just stored everything as a bytes, right? So they came about. These people are coming about because they found that the complexity of the operating systems were becoming harder and harder. So they had to come up with this simple stuff. And turned out that Unix was a big hit. I mean, because we're still using that as some sort of a modern operating system, but it came out of that kind of a work, right? And if you follow the operating system discussions, people still want the good old days back. I mean, people never stopped asking for those, right? How many of you follow what happened with Vista and whatever the file system they had, right? You remember the?
It was a database officer, right?
Yeah. So they wanted to come with a database file system. I forget WebFS or WinFS, I think, right? I think WinFS, right? WinFS was supposed to be the modern stuff, which would give you database semantics inside the file system, right? But that idea has been around for a long time, and around this time is when people started to realize that having all this complexity maybe is good, but then it becomes too complicated kind of stuff, right? But it's a lot of exciting time because you see all the stuff happening, and from a OS perspective, now it's not a very exciting time because people still get excited about Unix and stuff, which is not that. I mean, it's pretty old, right? They were trying to come up with ways of using this computer, this expensive stuff, right? If you read the Unix paper, they say they were able to develop Unix because they could find this cheap computer sitting in the basement, right? It's only $40,000, right?
Yeah.
It was $40,000, not in today's dollars, but in 1970s dollars, 60s dollars, right? And $60, 40,000 is probably a lot now, right? I don't know what the exact change would be. But it was cheap. It was cheap compared to other machines, right? So this machine, I don't know how much it cost, but it's probably more than $40,000, right? So you have this large piece of equipment. Until that point, it was sort of used for the cool people doing a lot of important stuff. They were trying to call it multi-programming or something to get more out of the system. So they're trying to argue that maybe you should be able to send something to the hard, you should be able to do more out of the system by letting it do more tasks, because these things tend to be very hard, right? And multi-service system is way off. I think what was important was they were trying to move it from a domain where people who had like all the resources, like money and stuff, were using it, to something that normal human beings could use, right? You need to have multi-programming and multi-user before people like us could use these systems just for the fun of it, right? Which kind of, I think, I would argue, spawned the PC world and all those things, right? If they had kept it as this computing device, which is being used for predicting the weather and all those things, the world would have been a lot different. But there was this attempt to make it not as cheap as what they used to, but what they had, right? Computers were very expensive until recently, right? Like I think early 90s when I was in grad school, Sun workstations cost like $50,000, right? Which is still a workstation, which is still not a mainframe, like whatever the desktops that you have in your offices and stuff, right? Those cost $50,000 and so, right? We knew that because when they're after their use, they're put on for sale in the surplus kind of store, right? If you operate in any school, the surplus, they depreciate it a certain way, right? So a 10-year-old machine was depreciated to, I think, $20,000, right, from $50,000, right? So they're trying to sell it for $20,000, a 10-year-old Sun workstation, and it's kind of ridiculous because you can buy like a new machine for like $1,000 or so, right? So anyway, the machines were kind of expensive. And so that's I think that's I don't think they even imagined that at some point you're going to be walking around with the iPhone, which is more powerful than what they were doing, and you can do different stuff, right? They didn't think about it. They didn't fathom that kind of world, because it still was bulky and still was, you had to walk over to a computer center and hand over punch card and stuff like that. But eventually the outcome was what we're trying to do, and they're beginning to understand the notion of how to solve the bugs, right? Before that, it was all about the best system you can build, and sort of the reason why you were doing that was the computers were expensive, right? If the university had to spend, say, $100 million to get a machine, right? They didn't want that thing which couldn't do anything, right? They wanted to dice and chop, and anything you can think of you wanted it to do, and then you kind of realize that you just can't do that. I mean, you just have to tone it down what it did, right? So that's the context. It's not that ancient, but it's still ancient from today's world. So now look at the notion of how were they relevant back then, right? Let's try to put ourselves in that context, right? How was semaphores? They're pretty happy with it. I mean, they developed something with it. It's surprisingly they understand a lot of stuff. I mean, they call it an unstable situation, which we probably call it as unsafe or deadlocked, right? Semaphores did pretty much what we do right now, right? Semaphores, it's a simple data structure in some ways, but they were trying to use it for something, right? Did it make a lot of sense in their time? Because I'm still not convinced that they had multiple processors. I think they probably wanted multiple processors at some point, but not that time, right?
Would they have had something like a math coprocessor? Or is that relatively new?
They used to have math coprocessors, but they were again another computer, right?
So what I mean is, could they be using level 0 or whatever as a level to do math coprocessing or some other coprocessing function? Instead of as dual cores or whatever,
yeah.
I think of today, or dual processing.
No, I think IBM's used to have the math coprocessor and IO processors as more of a peripheral.
So they wouldn't code it necessarily as a
No.
processor. They would code it as a peripheral or something.
As a peripheral. But there's no indication that this one had a thing like that. Yeah.
I'm just wondering, are they using semaphores to control I/O access?
They were, but it seems like it's awfully complex thing. How many of you programmed with semaphores? So if you haven't programmed with semaphores, so for people who program with semaphores, how do you like it? Is that your, if the world didn't know about semaphores, right? Would you choose semaphores to do it, or would you have to be forced into it by something?
Some fours are fine, but I mean, I only had to use them like once, so it's rare that you need them.
If you understand exactly what's going on, semaphores are good, right? I mean, I think one of the hardest part with all this synchronization stuff is you suddenly realize that you don't know much about what you're doing, right? You come to realization very quickly that like whatever you thought you could kind of wing it, you can't do, right? You could write a program, you can sit in front of the computer and probably write hello world, right? You don't have to look at all the stuff, just like do hello world, just compile it a couple of times, some code dump here and there, things start to work, right? But when you're in a situation where you need semaphores, meaning like you have multiple processors and say threads or something, semaphores become extremely hard, right? Because either you can make the system so linear, like basically serialize it with semaphores, that it's trivial to do and you get zero performance gain from having multiple processors. Or once you actually have this semaphores, it becomes extremely complicated, right? But they seem it's kind of hard to imagine how they came up with all this complication when it doesn't seem like they were really forced into it. But they also were very happy with it. I mean, they think that this will solve all of it kind of thing. Because I don't think they took the next step to more complex systems. And if for people who've done this right now, things are so complex that yes, semaphores are good, yes, semaphores are powerful, but we haven't mastered the technology yet. I mean, there's other things which we're still waiting for. And we see this in modern operating systems all the time. I mean, in modern operating systems, you still see deadlocks, maybe not as much in Vista and stuff, but going into multiprocessor, multi-core is still not that trivial because of synchronization issues, and so it's good that they came up with this stuff, but I still am not convinced that if my goal was to just build that dance system to do what they wanted to do, I don't think you would have gone with semaphores and all the abstraction. Right? We're glad that they did that because we can use that right now. So the layered approach, right? In their world, was that necessary? So in the layered approach, one of the nice things is you can have different layers which export certain primitives, but keep the mechanisms internal, right? So they can say, I will schedule processes to you, but I'm not going to tell you how. You ask me for a processor, I'll give it to you, right, at some point. And that's what you want to do. You want the layers to be completely independent of each other. They export the minimum amount of stuff, and then things should work, right? So how would you design such a layered system? Would you design it as a room where a bunch of people sit down and design the whole layers, or would you design it where there's like n groups designing n layers and go from there? Does that make sense? Should you be designing layer 0, what it should do, what the interfaces should give to other ones independently, or all one group sitting and designing all of the layers together? Yeah.
Seems kind of independently. The group should just have to agree what they want from the other group.
Independent, because there's the essence of abstraction, right?
Mm-hmm. Yeah.
But probably need some communication between different layers with your interface, you need to communicate.
Mm-hmm.
So,
Why do you need to communicate?
yeah, you need to call the lower layer to do something, right?
Yeah.
You need feedback.
Yeah.
Yeah, that's the problem. If you do it individually,
Mm-hmm.
how can you? First, we need the other interface between the layers, right?
Yeah.
Yeah, that's the point.
So I'm saying, no, like even if whichever way you do, right, you have to design what the interface to a different layer is, right? So if we discuss how to do layer 0, what they're talking about, right, we'll have to tell the layer 1 folks that our consensus is, we're going to give you these two system calls, or two, whatever they would call from that age, but like something, right? We call function 1 and function 2, right? Function 1 will do this, function 2 will do this, right? We're not going to tell you anything about what else we do, right? Right? So that's what will happen if you're doing separate groups, right?
Yeah, it's different level abstraction, like the network, different layer of code, right? This just imagine that there were 6 layers right there.
Well,
Also,
the problem that they're facing is if you took networking, it's exactly the same thing shows up, right? These are not nothing to do with the operating system. These are to do with building large systems which talk to different people, right?
yeah, that's the
Right? I mean, so if you look at networks, you see the same kind of issues, right? I don't know what the answer to that one is, because I think you would logically think that what should happen is you should have each one independently talking, not talking to each other, and come up with the best way. I mean, like what the lamps and paper was talking about, right? Do one thing and do it best, right? So we will have to say, layer 0, what we can do is with these two functions, we can do what is best for us, and we'll give you the most optimal stuff, right? And layer 1 folks will do the same thing. They'll provide something to layer 2 folks, but they need to get something from layer 0, right? Layer 1 folks need to take layer 0, right? So it's tempting for them to come and say, well, you guys did layer, function 1 and 2, but if you can give us function 3, which would make our life a lot simpler, right? Right? If you had one room where everybody's sitting, ideally you can all sit and discuss all the stuff and come up with the bus function which solves all the problems. So you understand the whole problem, right? So you know which thing should go where. You are optimizing for the whole system by doing these different layers together, right? But when systems get complicated, you can't do that. I mean, you can't imagine one person sitting and designing Windows Vista by saying, this is what should go in layer 0, what should go in layer 1, right? But once you start polluting each layer from the concerns of the other layer, right, then a lot of these benefits sort of go away, right? So ideologically, I can say the layers should be separate. They should remain what they're talking about. But practically, in networking, they call it cross-layer adaptation, right? Which is a nice form to say we pollute the different layers to do the same thing. Yeah.
Yeah, I think that question is pretty tricky, Probably their design approach, their developing approach is very good, actually. They have a concept stage, developing stage, and verification stage. I think at the first stage, it's called the conception stage. They probably whole group design what layer do something, and then in the construction stage, they probably, one group do this layer, the other do that layer. Well, that's my guess. I don't know.
But if they understood all the stuff, right? So you would argue. I mean, from there, I can't imagine why they would need layering at that level, right? There are 5 people designing the whole thing, right? They talked about it. It's not like they just went on and did the stuff. They talked about it and did the stuff, right? They could have done it without the layered approach, right? Yeah.
But I don't know if they would be able to prove correctness without the layered approach. The testing of the system was very, very easy due to the fact that each interface had to do something very specific, and they could test each interface one on top of each other and basically inductively prove, well, level 0 works, so since level 0 works, any functionality that breaks when we add level 1 is level 1 functionality that's broken, and kind of go that way. So I think the layered approach is actually very good for what they were trying to do, which is give a provably correct system.
But I thought that they kind of backed off of that by saying, once you have 2 layers, you can't say that, once you add the second layer, you get a bug. You can't really say it's the layer 1 bug, right?
Right. But it does help immensely, assuming that you could, but this assumes you could test everything, but since, as they pointed out, you actually can't test everything, so they are kind of making assumptions based on the test cases that they have are representative of all the test cases possible. And you can't necessarily make that claim, but that's kind of what they were saying.
So it's very nice, right? They're fathoming. They're trying to understand the issues that, with 40 years of experience, right? this argument is not over, right? This argument of where, how you should do the layering and where things should be. I mean, we'll see that the kernel is essentially a modern term for, I would argue, for layered, right? You don't call it layers. You have these, you have one layer, the other layer is, they communicate with each other. So you don't have the strict hierarchy where layer 0, layer 1, layer 2, but you have this layer 0, which is the microkernel. And layer 1 and layer 2 and layer 3, they can either talk hierarchically or talk amongst each other through some communication mechanism, right? And one of the best examples of the microkernel was Mach, right, which is the basis for the Mac OS X kind of thing. And even there, they wanted to build this operating system which is completely, they have to figure out what goes in the microkernel, what goes in the application level process, right? But nobody has the time to start from scratch and design an operating system. So they took Mach 2.5, which is essentially a monolithic kernel, laid it out on the table, and said, okay, draw a line and say, so this goes into the kernel and this goes into the user level process, right? So the line kind of looks jagged, like congressional district kind of thing. I mean, it's going all over the place because they didn't have the time to make a clear interface, right? And then over the next decade, they kept spending time moving stuff from here to there because performance was bad, so they're trying to do this stuff. So even though in theory it's supposed to be this clean, small interface doing all this stuff, in practice, it's, you kind of move stuff back and forth to kind of get good performance. It's not really a thing, right? Okay, you're saying something.
I think also logically, I'm not sure if any of them had made such a large system before. And when you're programming such large systems, it helps just your mental model to be able to think in a layered way. Mm-hmm. So that might actually have contributed to their success, their ability to realize that they might not be smart enough to view all the layers.
So I think what happened with Multics, which was sort of using a layered approach in a different context, I think Multics was probably killed by designed by committees, right? They probably had layers, and each layer was probably thought through by different companies, which had different motivations for different layers to be some things, and it's good to be a dictator in one sense, right? Good to say what should go on each one of those things, and taking layer too much too far, then you end up with that kind of issues, right? And the page relocation. I mean, they talk about page relocation, like move it in certain parts of the drum and move it away and stuff like that, right? From our perspective, it seems like when you have such a really awful system, why bother to do too much I mean, I'm not saying that you need virtual memory, right? Because 32K is the main memory, but it seems like they were shooting for a system which was not what they were actually working on, but their goal was to make their system that they have do all the nice stuff, right? The reason why this, I think, is in the Hall of Fame is they addressed issues which were ahead of their times, but it's not really clear how it was relevant to them, right? But that's the thing, right? But more importantly, so how are they relevant now, right? Why do you think this got into the Hall of Fame, right? And we'll see some of those things. We'll see they're not called the layer approach. We call the microkernel, monolithic kernel kind of thing. Essentially, trying to how do you organize the operating system either as one thing which does everything, sort of layered within this one space, or have kernel do something simple and then move everything to application level, right? We still don't know which way to go, right? Microkernels look really good on paper, right? Nanokernels look really good on paper because if I argue, yes, if I can move the absolute core down there and make it as fast as possible and move all the complexity up, then I win, right? But the practical aspects of that is how do you decide which should go where, and how can you be sure and say it should be in layer 0 and